All right, guys, before we get started, are there any questions over the homework? Any questions over the homework assignments? Now, you will have to add this to your note sheet because simplest form. There's three main things we need to focus on. Simplest form with radicals. All right, guys, let's focus in. Simplest form with radicals. You'll need to write these down. No radical can have perfect power factors other than 1. So we can't leave something as the square root of 8. We have to simplify it to 2 square roots of 2. If there's a factor, if there's some way that we can reduce the radical, we have to reduce it. We have to simplify it down. Another example of this would be the cubed root of 16 would be 2 cubed roots of 2. If we can reduce it, it needs to be reduced. No radicands, no radicals can contain fractions. We cannot have the square root of 1/2. We have to simplify it, and when we do simplify it, we end up with 2 square root of 2 over 2. We cannot have a radical or fraction inside of a radical. We have to simplify it down. We have to reduce it. And lastly, no radical can appear in the denominator of a fraction. 1 over the square root of 3, doesn't matter what that radical is, we cannot have it in the bottom of a fraction. If a radical can be simplified, we have to simplify it. That's that first main simplifying property. Second one, radicals cannot contain fractions. I can't have a square root, cubed root, fourth root of a fraction inside. All right, guys. Make sure we're writing these down because you'll need these. And no radical can appear in the denominator of a fraction because if any of these show up, we will have to simplify. We do have to rewrite it. All right. Properties of radicals, these you already have down on your note sheet. The product property says if I have two things being multiplied together inside of a radical, I can split it up to those terms inside of radicals being multiplied together. Sometimes splitting them up is going to make it easier to simplify. The opposite is true. We can actually multiply two radicals with the same index like radicals and multiply what's inside. So we can merge them together. Quotient property says if I have two things being divided inside of a radical, I can split it up into two radicals being divided. Or if we have two radicals with the same index, the same radical being divided, we can merge it into one. The only reason we would really want to merge it into one is if the two numbers inside will divide nicely, will simplify nicely. 162 over 2, 162 is divisible by 2 evenly. We would want to reduce it. So let's look at these first few here. Cubed root of 12 times the cubed root of 18. 12 and 18 do not have perfect cubic roots. There's not a number or a factor of either one that can be multiplied by itself 3 times. So what we want to do is our factor trees. We want to see what the prime factorization of 12 and 18 is. So always look at prime numbers other than 1. So, and I always start smaller to bigger. And the first prime number that we know that goes into 12 is 2. And it'd be 2 times 6. Now the reason I use prime numbers or start with prime numbers as one of the factors is it makes sure this tree only grows in one direction. Because 2 is prime, it doesn't simplify any further. However, 6 2 is still a factor. It would be 2 and 3. Now, because we have found all of our prime factors, 2 and 3 are not factorable any further. Our prime factorization for this here is 2 times 2, or 2 squared, times 3 to the first. So for 12, our prime factorization is 2 squared times 3. And if we wanted to at this point, we could replace the cubed root of 12 with the cubed root of 2 squared times 3. And this is part of the reason why we can't simplify the cubed root of 12. We need 3 factors of either 2 or 3. Here we only have 2 factors of 2, 1 factor of 3. There's not enough. If we look at 18, well, 18 is still divisible by 2. It'd be 2 times 9. 9 is 3 times 3. Telling us that the prime factor of 18 is 2 times 3 times 3, or 2 times 3 squared. Questions on how we've done any of this here so far? We good with everything so far? Now, we can also see why we can't take the cubed root of 18, because it's the same as the cubed root of 2 times 3 squared. I only have 1 factor of 2. I only have 2 factors of 3. For us to be able to take a cubed root, we need 3. Groups of 3. But according to our previous radical property, our product property, if I have 2 like radicals being multiplied, we can multiply what's inside. So that's telling me I can take the 2 squared times 3 and multiply it by our 2 times 3 squared. Both like radicals, so we can multiply what's inside. And as we multiply these here, 2 squared times 2, I now have 2 being multiplied by itself 3 times. Our 3 times 3 squared is going to be 3 multiplied by itself 3 times. Now from here to simplify, there's a few ways we can go about it. One, just like we put them together, we can take them back apart. Because this is the same as the cubed root of 2 cubed times the cubed root of 3 cubed. And what is the cubed root of 2 to the third? This would be cubed root and third power would cancel, yes? So it's just going to reduce to 2 times cubed root of 3 cubed would be 3. 2 times 3 is 6. Again, once we get to this point, there's many different ways we can do this. As we went over on Friday, or on Thursday, since both of these have the same exponent, I can pull that exponent out, our power of a product. Then our cubed root and third power would cancel, leaving us with 2 times 3, which is still 6. There are several different ways we can get to this answer. Any questions on what we did here? Since we got an integer answer, that means the calculator can do it nicely. Any other questions on A before we look at B? 4th root of 80 divided by the 4th root of 5. Well, we know the 4th root of 5 is not going to simplify nicely because there's not a number, an integer number multiplied by itself 4 times. That's going to give us 5. But does 80 divide by 5 nicely? Can we get an integer solution? Well, yes. So we can use our quotient property to rewrite this as the 4th root of 80 divided by 5. Now for our simplifying steps, the third one, by doing this, we do not have a radical in the bottom of a fraction, which is fine. We can't have one, can't leave one there. But now we have a fraction inside the radical. Also can't have that. But since 80 does divide by 5 nicely, 80 divided by 5 is 16. We can divide those two, telling us that really we have the 4th root of 16. That is fine. And this would be simplified in simplest form as long as we don't have a perfect int root inside there. We don't have a factor of 16 that can be written as a number to the 4th power. Two ways we can do this. One is we can factor tree. Well, 2 is a factor of 16. It's 2 and 8. 8 would be 2 times 4. And 4 is 2 times 2. Can't go any further. We have 1, 2, 3, 4 2's, telling us that 16 is indeed 2 to the 4th power. So if we wrote this out, we'd have that the 4th root of 2 to the 4th, which is just 2. Again, that's a nice integer answer, yes? Means that calculator would do it just fine. Questions on the first two? 4th root of 128, or sorry, not the 4th root, the cubed root of 4 times the cubed root of 128. Well, as we've seen so far, there's a good chance we're going to grab that calculator. Tells us it's 8. So the correct answer is indeed 8. Now, if we wanted to work this out, we would need to write these in our prime factorization forms. Now, hopefully at this point, knowing that 4 is 2 squared, I think we have that one down by now. 128, on the other hand, might be helpful to be able to write it out. I have a feeling it's going to be a whole bunch of 2's because our answer is 8. Now we know we have 2 times 64. 64 is 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4, and 4 is 2 times 2. We got 1, 2, 3, 4, 5, 6, 7. $128 had a whole bunch of 2's. Luckily, it wasn't 256 because that would just be 2 to the 8. Double it again. Questions on this so far? Questions on anything we've done so far? Since I'm multiplying like radicals, we can multiply what's inside. So we're going to be multiplying 2 squared and 2 to the 7th. Now if we wanted to, I can come in here and we can say 2 squared times 2 to the 7th, and that would be perfectly fine. But if we're multiplying like bases, we're going to do what? Add the exponents, so 7 plus 2 is 9. So really what we're saying is we're taking the cubed root of 2 to the 9th. Two ways we can look at this. One, how many groups of 3 go into 9? How many groups of 3? 2's can we take out of 2 to the 9th? Or we can use the fact that the nth root of a to the x is equal to a to the x over n. A is still 2. If we rewrite this as a fractional exponent, the number on bottom is the root, the number in the V. And our root, our n in this case, is 3, so we're taking a third. X is going to be the number, the exponent attached to 2, which is 9. So realistically, we're looking at 2 to the 9/3. Well, what is 9 divided by 3? 3. So really, we're looking at 2 to the 3rd, which is 8. We get there either way. And because it came out to a nice integer number, that's why the calculator did it nicely. But either way works. Questions on how we did this one here? Fifth root of 192 divided by the fifth root of 6. Well, there's a good chance, like the last one, we could plug it in and we get an answer. But it is also true that 192 is going to be divisible by 6. I say there's two main ways that we can figure this out. One, a number is divisible by 6 or has 6 as a factor if it's divisible by both 2 and 3. 192 is definitely divisible by 2 because it's an even number. We know a number is divisible by 3 if the sum of its digits is also divisible by 3. So 192, 1 plus 9 is 10, plus 2 is 12. 12 is indeed divisible by 3. So it tells us 192 is divisible by 6. The other method, I grab a calculator and take 192 and divide it by 6 and see if I get an integer answer. It tells me it's 32. So this means that we're trying to simplify the fifth root of 32. We're trying to see what number times itself 5 times is 32. One way that we can do this is we can do a factor tree for 32, yes? Or I can look at the factor tree we just did. Already has it there for us. For our 32, we've got 1, 2, 3, 4, 5 2's. So we're telling me I have the fifth root of 2 to the fifth, which lo and behold is 2. So a lot of what we're doing here is just factoring, finding our factor, simplifying our radicals. Questions on these here? Well, at this point, cube root of 135, there's no reason not to just grab a calculator, plug it in, and let it tell us that the integer answer is, well, this one's not an integer answer. So we cannot take the cubed root of 135 nicely. And as long as it says to round, approximate, we're good. Here it says to simplify. If it's asking us to simplify, we need it in simplest radical form, which means for this here, we're definitely going to need to use the factor tree. I always look for factors, prime factors that I know that will go into there nicely. And well, since this ends in a 5, we know that 135, one of the prime factors has to be 5. We can grab a calculator and say 135 divided by 5 is 27. So 5 times 27 would work for this here. 27 is not divisible by 5, but it is divisible by 3. 3 times 9 is 27. 3 is prime, but 9 is not. It would be 3 times 3. Telling me that the prime factorization is 3 times 3 times 3, or 3 cubed times 5. So therefore, we can replace 135 with its prime factored form. So the cubed root of 135 is the same as the cubed root of 3 cubed times 5. And according to our product property of radicals, we can rewrite this as the cubed root of 3 to the third times the cubed root of 5. And what is the cubed root of 3 to the third power? It would be 3, because our cubed root in third power, because they match, they would cancel out, because that's the same as 3 to the 3/3 or 3 to the first. Because I only have one factor of 5, it does not simplify, it does not reduce, telling me that the cubed root of 135 in simplest form would be 3 cubed roots of 5. And if we wanted to make sure that was the correct answer, we could grab the calculator and say 3 times the cubed root of 5, and see that that is the exact same decimal answer as our cubed root of 135, so therefore they are equivalent statements. Questions on this here? Fifth root of 7 divided by the fifth root of 8. Well, based off the last one, this one's probably not going to simplify. And 7 is not divisible by 8. They don't reduce nicely. So the big issue with this one here is that we have a radical in the bottom of the fraction. Now, if I had, say, 8 to the 5th power, that radical in the 8 to the 5th would simplify nicely. But before we mess with 8 to the 5th or do anything with 8, I want to make sure that the numerator and denominator, there are no perfect nth roots. There's nothing that's going to reduce out. Because if we multiplied by 8 to the 4th on top and bottom, we would have too many factors. Because 8 is not prime. Because according to the factor tree, 8 is 2 times 4. But 4 is what? 2 times 2. Telling us 8 is actually 2 to the third. We can rewrite it, we can simplify it. So really what we're looking at is not so much the fifth root of 7 divided by 8. We can really think of it as the fifth root of 7 divided by the fifth root of 2 to the third. Because every time we have 5 factors of a number, we can reduce that fifth root. We can simplify it down, we can reduce it down. So if I'd have multiplied that 8 on bottom by 8 to the 4th, we would get 8 to the 5th. Because we would have a radical, it would simplify fifth root and fifth power. But really, we're not so much looking at 8 to the 5th. We would be looking at 2 to the 15th. That's 3 groups of 5 2's that we actually have. Which means the numerator, whatever we do elsewhere, would also have too many factors. So the first thing we want to do, especially with this here, is see, is that denominator term, is it prime? If it is, we leave it alone. If it's not, we need to see what are its composites, what are its factors that we can work with. Since we had 8, it has factors, it has 3 2's. We broke it down, we simplify it down. Now, what we're going to do is multiply the top and bottom by a fancy version of 1. Because we want that radical out of the bottom of the fraction, we're just rewriting it. Currently, we have 3 2's. And if we're able to multiply by something to get it so that the denominator is the fifth root of 2 to the 5th, that fifth root and fifth power would cancel out, simplifying that radical out of the bottom, yes? How many 2's do we currently have? 3. How many more do I need to get to my next factor of 5? 2. Because if 3 and 2, we get them together, we have a total of 5, yes? So that means I'm missing 2 2's. So if I multiply that denominator by the fifth root of 2 squared, we're multiplying like radicals, multiplying like bases. 2 to the third times 2 squared, 3 plus 2 would give us 5, or 2 to the 5th. Yes? But what we do on bottom, we also have to do on top. So multiplying the denominators, the fifth root of 2 cubed and the fifth root of 2 squared, would get us the fifth root of 2 to the third times 2 squared. 3 plus 2 gives us 5. The fifth root of 2 to the 5th. That's what we wanted. because the fifth root of 2 to the fifth, that fifth root and fifth power would simplify, leaving us with 2. Now we just need to make sure that numerator does not simplify. And the only way it would is if 7 had factors of 2. Is 2 a factor of 7? No, 7's prime, yes? So there's no way that we have a fifth root that we can take out of those factors. So we are going to rewrite it a little bit. I'm not going to want to leave it as 7 times 2 squared. Because 7 times 2 squared is 28. If it doesn't reduce, if it doesn't simplify, inside those radicals, we're just going to multiply it, simplify that number back to what it is without a power. So the fifth root of 28 over 2 is the simplified form of the fifth root of 7 divided by the fifth root of 8. And if we plugged it into the calculator, we will get decimal equivalent. Questions on this here? Cubed root of 500. Calculator's going to give us a decimal answer. So we're going to need a factor tree. What prime number goes into 500? 5? Yeah. Because it'd be 5 times 100. 100 would be 5 is going to work again, so might as well keep using 5. 5 times 20. 20 is 5 times 4. 4 does not, but 4 is 2 times 2. So if we look at our prime factors, we do have 2 twice, 2 times 2. So we can say 2 squared. And we have 5, 1, 2, 3 times 5 to the third. We're not looking at our composite numbers, we're just looking at those prime numbers. So it's telling us that 2 squared times 5 to the third is 500. Now we can grab a calculator, plug it in, and see, does 2 squared times 5 to the third give us 500? And lo and behold, it does. So with simplifying this radical, we can replace 500 with the cubed root of 2 squared times 5 to the third. And just like before, because of our product property with radicals, we can rewrite this as the cubed root of 2 squared times the cubed root of 5 to the third. Now our cubed root of 5 cubed would be 5. Anything that we would have left over inside, anything that doesn't simplify completely, we'd have to leave inside our cubed roots. Cubed root of 2 squared, since we only have 2 factors of 2, it does not simplify. So we would just multiply those back out, telling us that the cubed root of 500 is 5 cubed roots of 4. Yes. Questions on the cubed root of 500, getting it to 5 cubed roots of 4. Fourth root of 19 over the fourth root of 4. 19 does not divide by 4 nicely, mainly because 19 is prime. 4 is not prime, but at this point we know that 4 is 2 squared. Now, the reason we're doing this and trying to simplify it is to get that radical out of the bottom of the fraction. Currently, we have 2 2's, but for that radical to simplify, we need it to be 4. So what we're missing is 2 more 2's. Because if I multiply that denominator by 2, the fourth root of 2 squared, we'd have the fourth root of 2 squared times the fourth root of 2 squared. 2 plus 2 is 4. Our powers, those exponents of 2, would add together to give us the fourth root of 2 to the fourth, which is what we want because the fourth root of 2 to the fourth is 2. It's not always going to work out that the denominator is going to become 2. It just coincidentally worked out with these 2 here. In the numerator, we're still going to need to multiply our 19 and 2 squared. 19's prime. We don't have any common factors, because if we did, we would need to simplify those perfect nth roots out. Because if, say, 4 was a factor of 19, our 2 squared and 4 would give us 2 to the 4th, just like the denominator, and it would simplify. Although, if we did have a factor of 4 on top, we would have divided it out to begin with to simplify. So really, at this point, we can just go 19 times 2 squared, or just 19 times 4, telling us that the 4th root of 76 over 2 is our final answer. Questions on this here? Questions on anything we've done so far? We ready for the last type of problem? One over 5 plus the square root of 3. The issue with this here is that we have a radical on bottom. Not so much we're adding radicals together. We cannot have a radical on the bottom of a fraction. Now, what we're going to do is something that might seem a little odd, because we are going to multiply by 1. But what I'm going to do is I'm going to take a denominator, that expression, and switch the sign in the middle. Not the sign in front of the radical, but the sign between the 2 terms. So the 5 and the square root of 3, I'm going to switch that sign. Even if it had been the square root of 3 plus 5, I would have still switched it between the 2. And what we're going to do is multiply the 2 together. Now at this point here, I'm not so much focused on the numerator. Let's focus on the denominator first. So when we distribute this through, the first thing we're going to do is 5 times 5, which is 25. 5 times negative square root of 3 is going to be negative 5 square root of 3. Because the only way we can multiply what's inside radicals is if we multiply 2 like radicals together. So that 5 has to multiply with the negative 1 in front of our square root of 3, negative square root of 3. Now we're going to do the same thing with square root of 3. Square root of 3 times 5 is going to be plus 5 square roots of 3. And lastly, square root of 3 times negative square root of 3. Positive times a negative is a negative. Still have the square root. Multiply what's inside. 3 times 3 is what? 9, yes? Normally, in a lot of cases, we'll see this in 5.4 when we multiply radical expressions. When we have expressions in the radical, we'll just write it out and multiply in the next step. But here, 3 times 3 is 9. Now the question is, well, we wanted to get rid of radical terms. We wanted to not have any radical terms in the bottom of the fraction. We went from 1 to 3. But before we second guess what we did, let's see what happens here. Negative 5 square roots of 3 plus 5 square roots of 3. I had negative 5 of them, and I had 5 of them to it. So we have a total of 0, yes? So those would simplify out. We still have 25 minus, what is the square root of 9? So by multiplying the denominator by 5 minus the square root of 3, we ended up getting down to 25 minus 3, which is, by multiplying by the irrational conjugate on top and bottom, the denominator is radical simplified out. We don't have them anymore. We still need to multiply the top. Questions on this here before we multiply the numerators? So on top, we're going to have 1 times 5, which is 5. And 1 times negative square root of 3 is negative square root of 3. Well, 5 and negative square root of 3 are not like terms. telling us that our final answer is 5 minus the square root of 3 all over 22. If I got an inkling and just felt like it, could I also say that this is negative square root of 3 plus 5? Are those like expressions? Yeah. Questions on what we've done so far? So we feel comfortable with this here? And there's no reason I would ever show you how to do something by hand we couldn't do in a calculator? Of course, your graphing calculator is going to give you a decimal approximation every single time. Because if we did this one here, we'd have to multiply it by the square root of 2 plus 5 square roots of 3. Now the numerator would be nice. 4 times square root of 2 is 4 square roots of 2. 4 times 5 square roots of 3, 4 times 5 is 20, so we have 20 square roots of 3. On bottom, the square root of 2 times the square root of 2 would be the square root of 4. Square root of 2 times 5 square roots of 3, we'd still have the plus 5. But square root of 2 times square root of 3, 2 times 3 would be 6. Negative 5 square roots of 3 times square root of 2. Incidentally, would be minus 5 square roots of 6. And lastly, negative 5 square roots of 3 times 5 square roots of 3. 5 times negative 5 would be negative 25. Square root of 3 times square root of 3 would be 5. Now, unlike the last one, we do have a lot more radicals on bottom. However, the square root of 4 is 5 square roots of 6 minus 5 square roots of 6 is still 0. Negative 25. Square root of 9 is 3. $25 times 3 is going to be negative 75. P minus 75 is negative 73. Now the calculator, what it's going to do is it's going to take that negative and factor it out of the denominator. It's going to pull it out of that denominator and multiply it through the numerator, giving us negative 4 square roots of 2 minus 20 square roots of 3. It does this so that we don't necessarily have a negative on the bottom of the fraction. Might leave it there, it might not. It also decided to put the square root of 3 in front. Same exact answer. And that is it for 5.2. All we're doing in 5.22, we only have one more section of 5.2 that we're to cover, and then 2 sections of 5.4, and we are finished with chapter 5. What that is.